Okay, well, it's time to get started. I'd like to welcome you all to the first BIMR Seminar of 2023. For those that don't know me, I'm Alex Agarnow. I'm the director of the Ferroelectric Institute, and it's a great pleasure for me to introduce the first speaker in a series of talks that are coming up by new members to the Institute. So mostly new faculty members to Nanoscale, some more established faculty members that are just new to the Institute. But today, it gives me great pleasure to introduce Gitanjali Kolhatkar from the Department of Engineering and Physics. Professor Kolhatkar did her bachelor's degree and master's degree in physics at the University of Ottawa, and then carried on to PhD studies at the University of Sherbrooke in electrical engineering, finishing her PhD in 2014. After that, she did a postdoctoral fellowship at the IMRS in Montreal, I believe.
Yeah.
From 2015 to 2019. And then was an invited professor at the Munich University of Applied Sciences for about a year or so, after which she held a prestigious Humboldt Fellowship at the University of Kiel, also in Germany. And last year, we were fortunate to have her come to join us at McMaster University in the Department of Engineering and Physics. Yes, started up her independent career. And today she's going to tell us about her research work that involves smart materials for artificial synapses, self-organized learning and pattern recognition, and nanoscale imaging. So please.
Okay, thank you very much for the introduction. So today I'm going to talk a little bit about the research I've done and the research program I'm planning on establishing here at McMaster. So my research program focuses on the development of artificial synapses that can learn just like the human brain for the next generation of computers. So I'll start by explaining the motivations of my work. So I'll talk about the current deep learning algorithm and how they consume a very, very high amount of energy. And then I'll explain how it will and why it would be interesting to develop some hardware that can learn and think just like the human brain in order to reduce significantly this energy consumption. I'll then show some experimental results. So I'll discuss artificial synapses using devices called Ferroelectric junctions, and how we were able to image the materials that compose the field in order to understand a little bit better their properties. And then I'll conclude on the performances that we already got and how we can improve them further. So as most of you probably already know, computers can now learn and analyze data so that they can even recognize some patterns. So those patterns can be, for example, shapes, voices, trends, colors, and so on. And those pattern recognition algorithms are now exploited in everyday life. We all use them on a daily basis. Whether we're talking about autonomous vehicles, security, telecoms, even the economy when predicting the stock market, the Internet of Things, as well as energy and solar panels, or even prosthetics. So they're really everywhere. Nowadays, algorithms that allow the computers to perform such pattern recognition exploit the current computer architecture, which is based on what we call the von Neumann architecture, which is illustrated here on the right, where the CPU and the memory are separate. The process is done in series in this case, which results in very long operation times. This also leads to a very high energy consumption and therefore a very high carbon footprint. So for example, it takes about 13 kilowatts for a supercomputer nowadays to perform one single narrow training operation. This results in a very high carbon footprint of up to 12 kilograms of CO2 for a 36-hour training operation in Canada. So those values depend on when we are in the world, and those are the ones for Canada. In comparison, our brain can perform parallel processing and is not restricted to series processing. And it does that while using a very, very low amount of energy. So, for example, our brain uses 20 watts to perform the entirety of its operations in parallel, which is significantly lower than the 13 kilowatts we just discussed. Therefore, the brain provide a means to significantly overcome these drawbacks and perform those pattern recognition operations with a very, very low amount of energy, close to that of the human brain. But first, in order to understand how to make those artificial synapses, we need to understand a little bit how the human brain's neural network works. So, for example, let's see, we look at a shape. For example, this letter 6. And we're going to try to remember it and recognize it later. So we're going to look at this 6 and we're going to see it. And then our brain is going to do something. So our neural network is composed of neurons that are interconnected by synapses. So on this schematic, we have the two big neurons on either side. And at the interface, we have a synapse. Our ability to learn is done through due to a strengthening of the synapses. Therefore, when we see this 6, a synapse will become stronger, so that in the future, when we see this 6 again, we'll be able to recognize it. So we want to make a device that can reproduce the same behavior. But before doing that, we need to learn a little bit how pattern recognition actually works. So let's say we have a picture that will be our input. So here we have two different pictures, that of a cat and a face of a human. And our brain is going to try to see which one is the one of the cat, which one is the one of the human. So our brain is trying to answer the question, is that the face of a human? And to answer this question, it will go through a series of verifications. For example, it will check, does the face have eyes? Does the face have a mouth? Does the face have a nose? And we will provide an output, yes or no, the face is that of a human. And this concept can be generalized by talking about an artificial neural network. So those of you who are familiar with machine learning, this is a very a concept that is very widely used in machine learning. So here is an illustration of an artificial neural network. So it's composed of a series of nodes that are interconnected. And those nodes correspond to different layers. So we have the first layer that will be the input layer. And that corresponds to the face that I showed you in the previous example. This could also be represented as a voltage. The next layer is the hidden layer. So it corresponds to the verifications that I presented before, whether the face has some eyes, a mouth, and a nose. And that can also be generalized by talking about a current. And then the last layer is the output layer. Yes or no, the face is that of a human. And those different layers are interconnected by a synapse. And this concept can be directly reproduced by fabricating something we call resistive memory crossbar arrays. So those crossbar arrays are illustrated here and consist of a series of a grid of two interconnected metallic electrodes. So here we have the first grid, the voltages, and the second grid corresponds to the input layer. At the interface, at the intersection between the two series of grids, we have a resistive memory device, which will serve as a synapse. Not taking this structure and just applying Kirchhoff's law and Ohm's law, we can say that the current is equal to the sum of the synaptic weight times the voltage. So this tells us that resistive memory crossbar arrays can directly reproduce an artificial network. That being said, I've been talking about resistive memory devices, But what is a resistive memory device? Device that can present something, a characteristic that we call resistive switching. In these devices, we can change our resistance by applying a voltage. So here is a typical current voltage characteristic that we can obtain on a resistive switching device. So here we have an IV curve, and the curves correspond to the results that we obtain on our devices. So we can see that we have an hysteresis with two different stable electrical states. In one of the states, the green one, the current is really, really low as we change the voltage. And on the red one, a significant amount of current can flow when we increase our voltage. So this red curve indicates that we have a low resistance, also known as low resistance state, where the current is able to flow. The green curve corresponds to a high resistance states, because the resistance in the material is so high that no current or almost no current can go through. Several types of resistive switching devices have been fabricated and reported, but among them, ferroelectric tunnel junctions have been identified as the strongest contenders for artificial synapses. So, what is a ferroelectric tunnel junction? So, as I said, this is a resistive switching memory with two stable resistance states that can be exploited for artificial synapses. And the device structure is very simple and can be seen on this figure, where we have a ferroelectric layer that is sandwiched between two metallic electrodes. And the only characteristic of the ferroelectric layer is that its thickness is not above 4 nanometers. So it's a very, very thin, or also called ultra-thin film. Here, those ferroelectric tunnel junctions have already been identified as good candidates for the universal memory. So the universal memory is a memory that combines all the advantages of DRAM, flash, and SRAM. So it has a low energy consumption, it's highly scalable like DRAM, non-volatile like flash, with a high speed just like SRAM. But now which material for this ferroelectric layer? So we identified a compound made of hafnium zirconium oxide as one of the strongest candidates for that. And that's what we synthesized and used for artificial synapses. So why this one? Because it is ferroelectric in its orthorhombic form, which corresponds to its crystal structure, so the arrangements of the atoms in the crystal. So this material displays some ferroelectricity, as we can see on this graph. So ferroelectricity means that by applying a voltage, we can switch the polarization from up to down polarization. On the bottom, what we see here is that as we apply a voltage, we induce a higher and higher strain in the material that will increase until it actually goes the other way and decreases. And we have that kind of behavior in the material. Because energy efficient for the material to switch it polarization. So this is what a ferroelectric material is, and this is what we need to use for our devices. So far, some models have attributed this ferroelectricity to the presence of grains in the film in a different crystal. Also, the hafnium zirconium oxide has the additional advantage of being compatible with the CMOS technology process, which makes it suitable for very large scale integration. However, the exact origin of the ferroelectricity remains unknown. So we synthesized this ferroelectric hafnium zirconium oxide using magnetron sputtering. So this is a deposition technique that is highly industry favored, as it provides a good stoichiometry control, a good layer homogeneity, and also a good reproducibility. So we started by fabricating hafnium zirconium oxide films with a 50-50 content. And the first step was to verify whether or not they displayed some ferroelectricity characteristics. So here is an image, a phase image corresponding to the phase of the polarization that we measured on one of our films using piezo response force microscopy. So here's the typical image we got, where the bright yellow region corresponds to a region where we applied a voltage of -7 volts. The dark region, also corresponding to the blue square, indicates a region where we applied +6 volts. So here we had a very high positive voltage, and on the other side, we had a very high negative voltage. We picked those two values in order to be sure that we could switch the material's polarization. So when we compare the two regions, we can see that we have a 180 phase change between the two, which confirms that we have a switching of our polarization. Now, we have the polarization pointing up. This is due to a change and a shift in the atoms that form the crystal. So here we have the orthorhombic crystal structure of our hafnium zirconium oxide. The green atoms correspond to the hafnium and zirconium atoms, while the red one corresponds to the oxygen atoms. So as we apply a voltage, we'll have a polarization that will point up. This is due to a displacement of the oxygen atoms towards the bottom, which in turn results in the polarization pointing the other way. If we apply this negative case, we have a shift of the oxygen atoms in red the other way towards the top. Now, in order to understand if those devices would be suitable for artificial synapses, we need to look a little bit more into what happens inside the devices themselves and the mechanism, the physical mechanism that take place. So here's again the device that we made. So here we have an ultra-thin ferroelectric layer between two metallic electrodes. A hafnium zirconium oxide is a very large bandgap semiconductor. It's a ceramic, and therefore it acts like an insulator. What that means movement. The presence of the two metals of the electron the potential barriers phi1 and phi2 have different heights. While I said that due to the presence of the insulator, the electrons will face a barrier which hinders their movement. Well, there is still a mechanism by which they can travel, and this mechanism is called quantum mechanical tunneling. And this mechanism states that if an electron faces a potential barrier, it has a finite probability of going through if the barrier is thin enough. So in order to have some current flowing, we need to have a very, very thin layer of 4 nanometers or less. Then the next step was to look at whether or not we could have some resistive switching in our devices. So just as a reminder, Resistive switching means that we have two different resistance states, and we can go from one to the next by applying a voltage. This is a typical IV curve that we obtain on our ferroelectric tunnel junction. You can see that we have two different states here. So the green curve corresponds to a state where a very, very low current can flow, and therefore indicates a high resistance state. This is polarization in our material pointing upwards. The blue curve corresponds as a function of the voltage that is applied. Low resistance. So this confirms that we have this resistive switching in those devices. Those two resistance states are also known as on and off states. And they correspond to the 0 and 1 logical states in binary code. Well, here is a schematic again of our device. And let's look at the potential barrier across the interface. When we're in the on state, screening effect. This accumulation of the negative charges will induce a decrease in the energy band and in the potential barrier at the bottom interface. Make it easier for the electrons to go through and will allow the current to flow across our device. The off state or the high resistance. Potential barrier at the bottom interface, which will make it more difficult and prevent the current from flowing. Now there are some tunneling that cross the barrier. The next one is the follow nodime tunneling. Result one is photon assistant mechanism relies on the presence of defects inside the ferroelectric layer. So these defects are usually due to oxygen vacancies, oxygen atoms that are missing from the crystal. These oxygen vacancies lead to the formation of traps inside our film. And these traps act as intermediate levels inside our potential barrier. Therefore, the electron can go through by going from one trap to the next. So all four mechanisms can be at play to understand which one dominates. Because understanding which mechanism dominates will allow us to better optimize our devices. So the 0 and 1 resistance states, the high and the low resistance state, confirm that the devices were suitable for non-volatile memories. However, as you probably know, our brains are not restricted to 0 and 1. We don't think in 0 and 1s. We don't have only two resistance states, but actually many different states in between. So now we needed to do more experiments to see if with those ferroelectric tunnel junctions, we could reproduce the behavior of the synapse with the ferroelectric tunnel junctions acting as a synapse. So to understand that, we need to look a little bit more into what happens when we're trying to learn. So when we're learning something, our neurons will fire a voltage pulse known as action potential onto the synapse. The change in resistance can be directly reproduced in our resistive switching devices. They consist in applying those voltages and measuring the change in resistance as a function of the time interval between the arrival of those two pulses. So we obtained a curve that looks something like this. So we have different regions. And let's look first at the region very far from the delta t equals 0. So in this area, the resistance change is negligible. It's pretty much 0. In the two, the cumulative voltage does not go beyond the threshold, which doesn't result in any change in the resistance. This is resistance. Now we can, what this graph also tells us is that we no longer have just two resistance states. We're no longer in just the 0 and 1 logical states, but we actually have a lot of data points in between with different resistance levels. This effect is known as multi-level. Shows that we can have multiple resistance levels instead of just the 0 and 1, more like what our brain does. So now, how does that compare to an actual biological system? Is this actually similar to what we see in actual synapses? So here on the left is a typical STDP that we obtain on a ferroelectric tunnel junction device. And this is a typical STDP obtained on the and the one obtained on the which tells us that our actinium zirconium ferroelectric tunnel junction can reproduce the behavior of a synapse. Then to understand more what happened in our devices, we developed a model. And this model is based on limited. So this model consists at looking at the polarization of the grains that form our films and associating that to a change in resistance. So here is the results of the simulations that we got. So what we see here is on the y-axis, we have the grain orientation. So whether the grains are closer to the low resistance state or the high resistance state. And we look at this as a function of the time, the two action potentials. So the black empty curve that we see here corresponds to the simulation model, and the green curve corresponds to the measurements. So using this curve, we started by comparing it or by getting an STDP, a simulated STDP curve, and comparing it to our experimental results. So that's what we see on this graph here, where the black dot corresponds to the experimental results, and the red curve corresponds to the theoretical curve. So we can see that we have So now when we look back here at the first curve, we can see that only a very, very small fraction of the grains is actually contributing to the switching. This leads to a very low change in resistance that we observe here. That is only about 0.1, which is significantly lower than what we would expect in our brain. If we look at plot that I show here, the voltage on top corresponds to the amplitude of the erection potential, more and more corresponds to the switch. So, we could reproduce the learning process of an actual synapse. But the resistance change that we see is still very low. And the response here, this area here, white, which indicates a slow response of our synapse. And this is due to some scientific aspects. The first one, the resistance change, is due to a low fraction of the material in the ferroelectric phase. And the slow response is due to a slow switching of the polarization within the grains. And all of this could be improved by understanding the origin of the ferroelectricity in our devices. So, as I said before, we still don't really know what is the origin of the ferroelectricity, but some models have been developed and proposed. And the models attribute this ferroelectricity in the presence of grains that form the film. So here's a schematic of the surface, of the film surface, and the grains that compose it. The idea is that the grains here are going to be in the tetragonal phase. But some other grains are the bottom, or like a rectangle with two different types. Those grains are adjacent to the other will make it so that they undergo some stress and they induce a stress on each other. This is the presence of ferroelectricity in the material. This has never been experimentally demonstrated. So then how can we confirm this hypothesis? Is there any way we could actually characterize the phase in the grains? So with this is the size of the grains. The grains are only of a few nanometers in size. So here is an AFM topography image that we measured on one of our hafnium zirconium oxide films. So the grains are, we can see them and they're very, very small, keeping in mind that this is a 200 nanometer scale. So they're very, very, very tiny. So we need a tool that can image the composition of those grains for such dimensions. So we have some optical techniques, such as Raman spectroscopy, that allow us to image the chemical composition in materials. However, those techniques remain limited by the diffraction limit. So you cannot have the information for structures that are smaller than about half a micron. So this makes it limited to special resolutions of a few hundreds of nanometers. Techniques have been developed to go beyond the diffraction limit and image surfaces at the nanoscale. And some of those techniques are known as near-field spectroscopy techniques. Those techniques consist in taking a metallic tip, usually made of gold, and focusing a laser at the interface, at the apex of the tip, sorry. The tip, just like in AFM, is placed in feedback with the sample surface. And the fact that we focus the laser at this interface will generate what we call a near-field amplification. So that means that, for example, the Raman signal will be significantly enhanced. As a result, we can obtain both the chemical and the structural information with a special resolution similar to that of an AFM, which is of about 10 nanometers or less, way below the diffraction limit. So here is a trivial example of a enhanced Raman spectroscopy configuration, where the Raman signal is enhanced. This technique can be applied onto a variety of materials, whether we're talking about 3-5 semiconductors, carbon nanotubes, DNA, and polar oxides. So we exploited this technique First, to study material that is very well known. So we looked at lead titanate, which is one of the most commonly used ferroelectric materials. And in order to check the potential of this just technique, we looked at nanostructures. So here's a schematic of the samples that we looked at. So the yellow areas correspond to the lead titanate nano island, which were deposited onto a platinum substrate. So we took our metallic tip, our gold tip, focused a laser at its apex to generate a near-field amplification and enhance the Raman signal. Here is what we obtained. So we measured simultaneously the topography, which is presented on the left, and the Raman signal, which is presented on the right. So the yellow regions correspond to the lead titanate nano island on the topography. And here we can see that we can observe the same islands as shown in the green regions. So we got a really good correlation between the topography and the chemical image, and we're able to image these lead titanate nano islands. Now, if we look at the spatial resolution here, this is 200 nanometers. So that means that each pixel is about 10 nanometers or less. We then try to push further the spatial resolution. So we focused on one of the islands in the white box, and we imaged it. And so in this image, we obtained the following image, and this corresponds to 60 nanometers, which tells us that each pixel is about 3 nanometers. So we really clearly see so that's great, but it doesn't give us any information regarding the crystal phase of the material. So then we looked at we wondered if there was any way that we could actually get this information. And to do this, we looked at the signal of the gold tip itself. Because gold also has an emission in this case. And the signal of the gold tip is Lorentzian shape, as we can see here. And it depends on the surrounding medium. So here we have 3 examples where the blue one is in silica, the red one is in water, and the black one is in air, all 3 of which have a different refractive index. So this shows us that the gold emission will shift the refractive index of the surrounding medium. So we then tried to apply that and test if this works on a known sample. So this sample was made of 3-5 semiconductor, and we had which displayed a topography that we can see here. So we could see some islands in the surface, as seen as the white-gray regions. And this is a schematic of the surface where we had islands separated by pits. So we attributed this to phase separation, where the pits were made of aluminum nitride, while the islands were made of aluminum gallium arsenide. Those 2 materials have a different refractive index of almost 2. Therefore, if we image the gold emission in the pit and on an island, we should expect to see a shift in the gold emission. This is what we obtained. So here is an image of the position of the gold signal as a function of the position on the surface that was taken simultaneously with the topography. So we can see that we got a very good correlation between the 2, where the red regions correspond to the islands, and the blue-green regions correspond to the pits. So now when we go from the top of an island to a pit, we can see a shift toward the lower wave numbers on the gold emission, which indicates a decrease in the refractive index between the 2 media. And this image was obtained with a very low spatial resolution of 25 nanometers. So this shows us that we had a technique that could go beyond just imaging the chemical composition, but also at composition changes and refractive index changes. Now we then wondered, between the different crystal phases in our ferroelectric material, should we expect a change in refractive index? So the answer to that is that yes. And we went back to our lead titanate nano islands. And these lead titanate nanoislands have been predicted to have what we call a core shell structure, where the core is in the ferroelectric phase, which means that it's in the tetragonal crystal phase, while the shell will be in the cubic phase. So we tried, both of these phases will have a different refractive index. So what we did now is that we took those nanoislands and we imaged them, this time looking at the shift in the gold emission. And we got the image that we see here. So we can see again very clearly the grains that form the nanoisland. Some region in really light blue. The side, which indicate a change in the refractive index. This shows us, or that this confirms that the grains are in the ferroelectric phase, while the shell is in the paraelectric phase. This confirms that with this technique, we were able to image the different phases in the nanograins with a resolution, very high spatial resolution, down to 3 nanometers. Now, the next step would be, can we use this technique to image the grains in our hafnium zirconium oxide ferroelectric films? And this is something that hasn't been done yet, and that would be an step. And getting this information regarding the grain structure would permit us to improve its ferroelectricity and fabricate more efficient artificial synapses. So in conclusion, we synthesize some ferroelectric hafnium zirconium oxide, and we use it to fabricate some ferroelectric tunnel junctions. And it's already identified for non-volatile memories because they are CMOS compatible, which makes them suitable for large-scale integration. We then went further and looked at their potential for artificial synapses that have the ability to learn just like the human brain. And by looking at spike time-independent plasticity measurement, we were able to confirm that those devices had indeed the potential of mimicking the behavior of synapses. However, the resistance change remains fairly low, while the response time also remains very slow compared to that of our brain. And this could be further improved by improving the quality of the material, which will be done by probing into the material structure and trying to understand it a little bit more in order to control it and to tune it to specific applications. So for the perspective, we'll be now looking at how we can increase the fraction of grains that are in the ferroelectric phase in our material, probe the micro and nanostructure in order to understand the origin of the ferroelectricity, and investigate parameters of our STDP experiment in order to see how they affect the multi-level switching and see if they can be used to further improve the behavior of our synapses. To thank my collaborators and the funding organisms. Also, since I'm a new professor here, I'm starting my research lab. So if you are interested or know anyone who would be interested in graduate studies and working on fabricating the next generation of high efficient computer that think like the human brain, as well as smart synapses, just don't hesitate to contact me. Thank you. Yeah.
How does it bring power consumption back?
That's actually a good question. I guess it would. So for this, we actually fabricated our own tips. So we took some gold wires and we etched them using a solution. And usually it varied, but we were around 30 nanometers. Yeah, roughly. Yeah. So yeah, so there's actually some variations. So some of them were 30 nanometers, Others were lower, so we got also some 10. One time we got 1, and then when we did the landing, it actually rolled on itself. Did some SEM after that, we're like, okay, so that really destroyed it. The way we also measure the radius of the tip, we actually have a model. And so we will scan some carbon nanotubes. And since the carbon nanotubes get information of the tip radius and the nanotubes. And with this, we actually go back to the radius of the tip. And then to get the resolution of the image itself, we actually look into the smallest features that we can get. And with this, we can extract, do some fitting and extract the resolution of the image.
So for your ferroelectric layer, right, you're just using zirconium, hafnium oxide.
Yeah.
Is that the only material that you use display? Are there others?
So there's others actually. So I also worked on the bismuth ferrite. Barium titanate also is one that is also very widely studied. The problem with those two is that they're not CMOS compatible. So we need the material to be CMOS compatible. Otherwise, when it goes through the entire process, then by the end, we'll have destroyed completely the ferroelectric film.
By CMOS compatible, what's that mean?
So that means stable under annealing of at 700 degrees Celsius under N2, I believe, nitrogen.
Okay, thank you for your talk. I have a few questions. So it's happening supporting 50-50%. Essentially, do you know the distribution? Is it full statistical distribution of hafnium supporting? Do you see kind of richer areas in hafnium, richer areas in zirconium? Related to this question, one of your objectives was to increase the fraction of the ferroelectric phase. That was more or less the last one. So what does it mean, really? So not all your field is ferroelectric?
So yeah, that's what it means actually. So we don't know the distribution of the hafnium and zirconium. That's something we didn't get the chance to look into. So we don't know about that. But yeah, it would be to actually have more of the grains that would be in the orthorhombic phase.
Okay, so I mean, the fraction is that it's not fully ferroelectric. In my opinion, it's not fully ferroelectric. You have a balance of ferroelectricity, balance which is not ferroelectric.
Yeah, that's the idea at least.
Is that established? What do you want to establish?
So that's what I want to establish. So that's our hypothesis. So by the model that we developed, that would tell us that only just a few of the grains are in this ferroelectric. Now, how many or anything like that, we haven't been able to characterize it.
I mean, my first suggestion would be just UPM and see how it's supporting.
Yeah.
Try to correlate to see what fraction you have. Do you know which one is more ferroelectric? Give you more ferroelectric properties that is happening in zirconium?
Well, it would be having the two, having this orthorhombic matrix where we have both hafnium and zirconium. But yeah, TM would definitely be something to look at.
I've noticed that we use two different electrodes. One is
yeah. Well, actually, yes and no. But so we need those two metallic electrodes to get this trapezoidal interface. So if we don't have that, we get a rectangular interface, and that doesn't allow for the electrons to go through. So actually, another design that we did, we use for both electrodes, and it ended up working. And in the end, so we didn't really understand why. We're like, it's supposed to be rectangular and could go through, and that's because we didn't preserve the vacuum during the entire deposition process. So we had no control over the oxidation of the layer, which made it so that we had two different interfaces, and our devices could still work because of that.
So let's pretend that you, as you said, we can build artificial synapses.
So from there to machine learning and pattern recognition, we know how to use this to implement these algorithms. We have ideas of the best model with a great change. So it's just
synapses at the interface. And now, while we are focusing more on the material themselves, other groups will use those and train them to actually see if they can recognize a number, for example. And the results are actually pretty good already. Yeah, yeah.
Okay, with that, let's end there and thank Gitanjali for a great talk.